Hi guys, nice to see you.
Hello.
Hello.
Hi. How are you doing?
Good afternoon.
Good afternoon. Hi.
Hello.
Hello.
Good afternoon.
Hi, nice to see you guys. Okay, so just short recall from our previous discussion. We introduced the conservation of linear momentum, like first linear momentum itself, and then we have shown for a closed system or quasi-closed system when external forces don't act on the system or external forces are compensated. We have shown that linear momentum remains constant of the system. Doesn't matter what events are happening, what type of collisions and interactions. If it's all defined by internal forces, the linear momentum of the system remains constant, which is quite fascinating by itself, and definitely very useful. So we also considered different types of collisions which are possible, like elastic, non-elastic, and perfectly non-elastic. So today we will continue with some description of collisions in two-dimensional space. So far we were talking only about like one-dimensional case, but now we will discuss two-dimensional space and consider some examples. And afterwards, depends on time, we will introduce the concept of center of mass and some basic examples with like applications of this concept to some systems we'll consider as examples. Okay, I think we can start since I believe everyone already had enough time to join us. Let me change to the slides, and we continue considering these collisions, but in two-dimensional space. So let us think about such a situation when we have mass m1, which moves with some velocity v1 along axis x. Then it hits some stationary body with the mass m2, so it doesn't move initially in any direction. And afterwards, obviously, we have some situation when we need to consider motion of these bodies in two-dimensional space. So let's say we have here axis y, here axis x. So at some point, which is point of collision, these bodies interact with each other and then they move in this two-dimensional space. So let's say it's one trajectory, this is another trajectory. So here is our mass m1, and it moves with some velocity vector v1 prime vector. And this prime stands for velocity after collision. So we agree on such definition. So here it will be mass m2, and also it moves with some vector, velocity vector v2 prime. These vectors, new velocity vectors of both bodies after collision, they will be aligned at some angles towards axis x. So here will be some angle theta, and here will be some angle phi. So now let us consider first like general case, and then map this general case on this particular situation in order to see what kind of set of equations we can get in order to describe this collision. So in general, we know that doesn't matter if it's elastic or inelastic collision, the conservation of linear momentum always works. So we can consider now it in two-dimensional space. So we will consider first projection of linear initial and final linear vectors, linear momentum vectors on axis x and then on axis y. And that let us write it in general case for two bodies. So it will be for axis x. We will have m1 times v1x plus m2 v2x is equal to m1 v1x prime plus m2 v 2x prime. So this is for axis x. The same we can write for axis y. So it will be m1 v1y plus m2 v2y equal to m1 v1y prime plus m2 v2y prime. Okay, so this is in general case because we need to consider both components of like both projections of linear momentum vectors of both bodies initially and finally. However, in this particular case, we need to think what we have and what we don't have. So let us write it for axis x. What is initial linear momentum vector projection on axis x? We have this m1 times v1, and v1 is in parallel to axis x and pointed in the same direction as axis x. So we can write that m1 times v1. Then we have stationary body m2, so it doesn't move. So this will be equal to 0. This component also equal to 0. And then we can write, describe the final situation. So we see here that we have m1 times v1 prime. However, we are interested now in projection of this linear momentum vector of first body, and actually also true for the second body on axis x, because we consider this direction. So that will be, we need to multiply this product with cosine theta. Cosine theta. Now we need to write for the second body. It will be m2 times v2 prime times cosine phi. Okay, so this is in particular for our situation, we have equation for axis x, which describes the conservation of linear momentum. The same we need to write for axis y. And here we see that this axis, this vector v1 is aligned perpendicularly to axis y, so its projection on axis y is 0, and m2 doesn't move anywhere. So in the left side, initially we have 0, which stands for initial linear momentum of this system along axis y. And after collision, we will have again two contributions from both bodies. It will be m1 times v1 prime. Now we need projection on axis y, so it's this part. And that is, we will get if we multiply it by sinus theta. The same stands for the second body, but here we need to take into account that this projection of linear momentum vector after collision of second body on axis y will be negative, because it will be like this. So it will be going in the opposite direction as axis y. So here we will get minus, and will be m2 times v2 prime times sinus phi. Okay, so now we already have set of two equations. And if there are two unknown, for instance, I don't know, like v1 and angle theta, and all other parameters are given, so we already can determine them, and these two equations are sufficient enough. However, if there is a statement that this collision is elastic, means that there is no conservation of kinetic energy into internal energy, we can also write equation which stands for the conservation of kinetic energy. And that will be m1 times v1 squared divided by 2. So its initial kinetic energy, second body was not moving, will be equal to the kinetic energy of the system after collision, because we assume that this is elastic collision. So it will be m1 v1 prime squared divided by 2 plus m2 v2 prime squared divided by 2. So in this case, we get set of three equations, and that already allows us to deal with three unknown parameters, which is great. So let us consider one example with two-dimensional like collision in two-dimensional space, when we have this perfectly inelastic collision, but carried out in two-dimensional space. So let us say we have some T-shaped cross section. And two cars are moving towards this cross section. So here we have m1 v1 and here we have m2 v2. So at some point in the middle of this cross section, they collide with each other and stick to each other, like start moving as a single piece. That means we have perfectly inelastic collision. we can attach our reference system to this point of collision, then it will be axis X and axis Y. So these are our cars after collision. They will move at some angle, let's call it theta, with velocity vector v. So let us see how we can describe this collision in two-dimensional space. This is perfectly inelastic collision in two-dimensional space. So projections on axis X. We have here which car will contribute to the linear momentum along axis X.
M1.
M1. That's absolutely right, because velocity v1 vector is aligned along axis X, and v2 vector is perpendicular. So projection will be equal to 0. So here we can write that m1 times v1 is equal, since it's perfectly inelastic collision, we will have sum of two masses times v, and that should be projection on axis X, so this will be cosinus theta. Now we need to write the same for axis Y. So here we'll be already contributing car with mass m2. It will be m2 times v2 equal to m1 plus m2 times v, and here will be already projection on axis Y, so it will be sinus theta. So if we take a look on these equations, and let's say we divide second by first, so it will be m2 v2 divided by m1 v1, then we will have here sinus theta divided by cosinus theta. So that is tangent theta. So that the ratio between linear momentum, initial linear momentum of like amplitude of linear momentum of first and to the second car will give us define this angle theta at which they will move after collision. And if we already have this theta, so we can substitute it in, for instance, first equation and get expression for the velocity, like speed of this motion after collision will be m1 times v1 divided by m1 plus m2 and times cosinus theta. So this is just an example of a perfectly inelastic collision in two-dimensional space. Before we proceed further with the center of mass, I would like to show you one interesting example of collisions. Let me share my screen. Yeah, do you see my screen now?
Yes.
Okay, cool. So you see such a common, widely spread toy, which consists of some stainless steel hard balls, which hang on some very thin ropes. And when we deflect one of these balls, then let it fly back to initial position, then this linear momentum which it gains will be transferred to the ball from the other side, will move away from the stack, and that will repeat back and forth for several times until, because of friction, it will not stop. However, the thing is that we always, if we pull one ball and let it fly back, only one ball from the opposite side will be deflected, like shown on this figure. There is never happening that if you hit with one ball and then two balls will deflect. So this is impossible case. And let us discuss a little bit about this. So from the point of view of linear momentum conservation, this is possible scenario. So we can consider we have, so mass of this, of each of these balls are equal. So we have m times v, and then we could consider, okay, let's have two balls instead of one. So it will be 2m times, we can just reduce the velocity in twice. So it will be times v divided by 2. 2 in denominator and denominator cancel each other. So we will get mv is equal to mv. Like m times v is equal to m times v. So in terms of conservation of linear momentum, it's completely possible scenario. However, any ideas why we actually don't observe such situation?
It's a conservation of kinetic energy.
Exactly, yeah, because we, as a model here, we consider this very hard stainless steel balls, which do not deform under this level of interaction, and we can neglect with conservation, converting kinetic energy into internal energy because of minimum deformation. So this is an example of elastic collision. And in this case, we also need to take into account the besides conservation of linear momentum, conservation of kinetic energy. So in this case, if for instance, we consider this scenario, we will get m times v squared divided by 2, its initial kinetic energy. And then what we have two masses, it will be 2m, 2 times m, times this twice smaller velocity, which will be v divided by 2 squared. So eventually we will get an equation m times v squared divided by 2 not equal to m times v squared divided by 4. So obviously this law of conservation of kinetic energy is not applied, so it's violated, and that's why this case is not possible. So if you want to see two balls deflecting from the opposite side, you need to initially hit it with two balls also from the left side. If you hit it only with one ball, then only this scenario is possible, and that is the reason because we have both conservation of linear momentum and kinetic energy. Okay, let me stop sharing my screen, and now we can proceed further and introduce this concept of center of mass. So in general, if we have some system of many bodies, let's say, or some continuous body, means with some random arbitrary shape, it is possible to find some point, mathematical point, which will be, if we describe the translational motion of this point, assuming that all mass of the system of many bodies or this continuous body will be concentrated in this mathematical point, then the description of translational motion of the system of these bodies and this single mathematical point will be identical. So then we don't need to describe motion of each body of the system. We can find this center of mass, assume that the whole mass is located, concentrated in this point, mathematical point, and then translational motions, instead of describing for all parts of this system of many bodies, we can describe only for the one mathematical point, which is the center of mass. So let us consider how we get the position of this center of mass. And obviously we start from single dimensional case, and then we will proceed to multi-dimensional examples. So let us say we have axis X and two bodies like X. So it will be body M1, body M2. Here is our origin of axis X, so coordinate 0. So position of body M2 will be given by coordinate X1. Position of body M2 will be given by coordinate X2. And our goal is to define where will be located the center of mass. So the approach how we do this X coordinate of the center of mass along axis X will be defined as M1 times its position along axis X plus M2 times its position, and divided by the sum of these two masses, M1 plus M2. So this is a particular case for two bodies, but we may have many bodies in the system. And that's why in general, we can write that X center of mass is equal to the sum of for all bodies, the product of their mass to their position, divided by the sum of all masses. So this would be marked as capital M. So we will have 1 over capital M times the sum of this product Mi xi. So this is the general case when we have many body system with how we define its the coordinate of its center of mass along one axis. If we have some three-dimensional distribution of these many bodies, obviously we need to define also additional coordinates for y and x, y and z axis. So for y center of mass position will be defined by 1 over m sum for all bodies mi times yi, and for the same equation we can write for the axis z. So it will be 1 over m sum for all bodies mi z I times the I. So now we can get coordinates in three-dimensional space for this center of mass, and quite convenient to define position of this center of mass with a position vector. So our position vector of the center of mass will be equal as xcm times I unit vector plus ycm times j unit vector plus zcm times k unit vector. So that is most general form how we can define this position of the center of mass. So this is valid for a system of many bodies. So when we have defined body and defined position for this given body with mass mi. However, there is also a possible scenario when we have some continuous body, some arbitrary shape. So in that case, we need to divide this continuous body in very small pieces, like small parts, with small masses which approach to zero. So as smaller parts we pick up, the better it is. And then kind of repeat this, the same approach, but in the limit that this delta m, this small mass, approaches to zero. So position for the center of mass for a continuous body should be defined as follows. Limit of delta m I, we can consider this, approaches to zero. Then we have 1 over total mass of the system times this sum for all these small parts of the body, delta mi times xi. So each of these small part of the continuous body will have its position, obviously within the arbitrary volume, like shape of this body. And this is nothing else as integration. 1 over m times integral x times dm. So for each position x within this arbitrary shape of the body, we will consider this integral x dm. So we will integrate all over the volume. So this is true for one coordinate. If it's three-dimensional case, we have some volumetric distributed body, then we can write that our position vector of the center of mass will be equal 1 over m times integral position vector of each of these small element dm, integral all over the volume of this body. Okay, so now I think we can do some examples, like how we apply this to some particular cases. And for this, we will consider two examples. It will be rod with uniform distribution of its mass, uniform linear distribution of its mass, and also a rod with non-uniform distribution of its mass. So let's have some axis x and a rod with some length L. We have a rod with constant cross-section, not as I drawn it, not very constant cross-section, but we believe it is. And here is the total length of this rod. Then in order to proceed with this equation for calculating the position of the center of mass, we need, since it's distributed body, we need to pick up some small element, which will be dx. at the position X. And we need to split this rod in many such small pieces and integrate according to the previously considered equation. So we also need to know linear distribution of its linear density. It's like kilos per meter. So it is considered to be constant. So it doesn't depend on X for this first case. Now, from previous slide, here we have this equation. Since we have rod, which is aligned along axis X, so it will be one-dimensional case. We will find center of mass along axis X. So this is the equation which we need to use. It will be X center of mass is equal to 1 over total mass of this rod times integral from 0. Sorry, no, that will be next. We will define it later. So will be X times dm. Okay, dm is not what we want to deal with. We want to express dm as a function of dx. So how can we, what can we write here? dm is equal
Lambda dx.
yes, lambda times dx. So we know this uniform linear density, and obviously if we multiply this linear density by small length dx, it will give us the mass of this small part of the rod, dm. So we can now substitute instead of dm this expression. This will be 1 over total mass of the rod integral x times lambda dx. And now we can already integrate along the length of the rod, and that will be from 0 to L. Lambda is a constant, so we can just take it out from the integral, and that will be lambda over, sorry, it's capital M, integral x dx from 0 to L. So this we will get lambda over M times x squared divided by 2 from 0 to L. Now, when we substitute these limits, we will get the following. Will be lambda times L squared divided by 2M. Okay, so looks like we already got it, but there is one more step. We also can express this total length in terms of lambda and length of the body, of the rod. So total mass is equal to lambda times L. So now let us substitute it here. Will be lambda times L squared divided by 2 lambda L. So we cancel out this lambda, cancel out square and lambda, and what we get, quite trivial result, that the center of mass will be located in the middle of this rod, which could look trivial, but we applied general approach to calculate this position of the center of mass, and we see that because it is a symmetric case, we have uniform distribution of its mass, lambda is constant, we get position of axis X in the center. So let us now consider another situation when, let me delete all this, when we have not uniform distribution of linear density. So it is some function of X. So let us write that lambda is equal alpha times X. So it will increase from X equals 0, like from 0 to some maximum value, which will be alpha times L. Okay, so we also have the same equation to deal with, and also go to this transition from dm to lambda times dx, so it's the same concept. However, we need to consider further that lambda is not constant, it's just alpha times x. So let us write it down. So it will be 1 over m integral x times, instead of, it will be lambda times dx, but instead of lambda, we write alpha times x dx. Now, alpha is a constant, so we take it out from the integral. And here we have range from 0 to L also. So we have alpha over m times integral x squared dx from 0 to L. So that will result in alpha over m times x cubed over 3 from 0 to L. So we substitute now L and 0 as ranges instead of x, and get alpha times L cubed divided by 3m. Okay, now we need to substitute the total mass. Any ideas how we get total mass?
Lambda multiplied by L.
That would be correct if we consider uniform distribution of linear density, so what we did previously. However, here lambda is not a constant, it changes along the distance. So in order to get the total mass for this particular case, we need to integrate from 0 to L over dm. And that will be integral from 0 to L. dm we substitute with lambda times dx, and we know that lambda is equal to alpha times x. So it will be alpha times x dx. Alpha is a constant, goes out from the integral. It will be alpha integral from 0 to L x times dx. And this is equal to alpha x squared divided by 2 from 0 to L. Eventually, we get alpha times L squared divided by 2. So this is the total mass of the rod. Now we need to substitute this total mass here in this equation for the coordinate of the position of the center of mass. So let us do it on the next slide. So what we have, lambda L squared divided by x cm is equal lambda L cube divided by 3m, and instead of m now we substitute expression of m. It will be lambda L cube divided by 3 times alpha L square, and then it was divided by 2, so we can put 2 in numerator here. So now, oh, sorry. That's not lambda, that's alpha. Here should be alpha. It was lambda initially when it was uniform. Alpha, and here also alpha. So with this, we can cancel out alpha, L square and this cube. And we see that for this particular case, for linearly changing density along this rod, position of the center of mass now will not be in the middle, in the center, but shifted it will be located 2/3 of the length closer to its edge. So if we have this rod with not uniform distributed linear density, which will follow this equation alpha times x. So for uniform, we have coordinate L divided by 2. And for not uniform, for this case, it will be shifted further, closer to this right edge. It will be 2/3 of total length L, because more mass will be located in this part, further from the origin of the axis X. So we see how it can be these rules for calculation of center of mass for continuous body can be applied in two cases when we have uniformly distributed density and non-uniformly distributed density. We just need to take this into account in the under the integral, and so that of course will depends how complicated this distribution is. So this is quite simple example when we have a linear distribution, but it could be some other more complicated functions. And then of course it will be more difficult to calculate. However, the concept is clear. We need to take this into account in the integral and integrate along the length of the rod in this particular case. If it's a continuous body in three-dimensional space, then we need to integrate all over the volume of the body. Okay, with this, I think it's everything what I wanted to tell you today. Any questions?
Yes, I have one.
Sure.
Can you show this for not just one dimension, but 2 or 3 dimensions in the next lesson, maybe?
Yeah, we can do that, but I think that we actually proceed. We also need to proceed further with the topic of moving with changing mass. That's another concept which like rocket case of motion when the body is losing mass while moving. So that is a topic to be discovered. And in this, for instance, if you have three-dimensional case, depends on which shape you have. Let's say if you have some sphere or cylinder, so you need to use the advantages of the symmetry of these bodies. And obviously you want to go for some polar or sphere system of coordinates. And then it's quite straightforward to do this integration all over the volume, because you will consider change in angle theta, change in d theta, d alpha, and then delta rho, which is change of the radius. So in this case, you have the range, for instance, for this three-dimensional case with the sphere, you have a range of changing angles will be for the x and y plane, it will be 2 pi, it will be 360 degrees. For the angle alpha, which gives position along axis z, will be from minus 90 to plus 90 degrees, from minus pi over 2 to pi over 2. And then change of the radius will go from 0 to r, which is the radius of the sphere. And with these ranges, you integrate you have like triple integral, integrate in the sequence one after another, and get integration all over the sphere. So that's how you can calculate, for instance, the volume of the sphere if you consider only dimensions. But if you have also, let's say, a mass product and it's continuous, so you operate with density, and density goes out from the integral. If density is not uniform around, like along this sphere, then you need to take into account the distribution of density, and that could be already a difficult case.
Okay, thank you.
You're welcome. But usually we deal with some uniform distributed cases. Oh, there is a question of difference between M and this capital M. So M is the total mass. Yes, exactly. So we have the sum of all, if we have a system of many bodies, capital M is equal to the sum of all masses of all bodies. Or if we have distributed system, then capital M is the mass of whole this distributed body, like continuous body. In case of distributed continuous body, we have delta M, which is just some small, which we divide this continuous body in small parts, and delta M is the mass of each of these small parts, which we push to the limit delta M approaches to 0, and eventually we get the integral. Okay. Thank you for attention. Have a good evening and take care. So see you on Friday, where we will continue discussing application of this conservation of momentum.
Thank you. Bye.
Bye.
Thank you. Goodbye.
Have a great
Bye.
evening. Bye.
Thank you very much. Bye.
Bye. Have a good evening.
Bye.
Bye.